When you look at a mountain shimmering in the distance, it looks like a permanent monument, solid, unmoving stone. But that stillness is an illusion. Mountains are actually violent, chaotic events unfolding in extreme slow motion. If you climb to the summit of Mount Everest, roughly 5 miles above sea level, you will find ancient fossilized sea creatures embedded directly in the rock. The highest point on the planet once was the bottom of an ocean. To get the seafloor into the sky, you have to look at the Earth's outer crust. It's broken into massive tectonic plates that drift a few centimeters a year, roughly the speed your nail growth grows. Over tens of millions of years, when two of these plates collide, the ground has nowhere to go but up. Flat layers of sedimentary rock get folded, buckled, and thrust skyward, layer stacked upon layer, like a rug pushed against a wall. Because our human lifespans are so incredibly brief, we are entirely blind to this motion. We look at a peak and see a fixed landmark, missing the active geology keeping that landscape alive. Once you know how to look at a mountain's shape, its silhouette becomes a readable timeline of its geological history. Jagged, razor-sharp peaks, like the Teton Range in Wyoming, tell you a mountain is young. The crust there is actively cracking on massive faults, violently thrusting new rock upward before ice and weather have a chance to wear it down. A near-perfect cone shape points to a totally different process. These are built from fire. Mountains like the Cascades are active volcanoes formed by repeated internal eruptions, piling up new layers of rock and ash from the inside over centuries. On the other end, the Appalachians appear as soft, rounded, forested ridges. They have been battered by relentless rain, frost, and wind for 300 million years, wearing their original towering heights down to gentle hills. And when millions of years of erosion strip away everything on top, you are left looking at the exposed rock roots of the mountain itself. The sweeping, sheer granite monoliths of the Sierra Nevada cooled slowly, miles underground, only exposed after the softer rock above them washed away. Every sweeping dome, sharp cliff, and forested ridge is an autobiography written in stone. It shows us exactly where the Earth is building itself up and where it is tearing itself down. But rock is only half the story. As you move up the slope, elevation dramatically alters atmosphere. For roughly every 1,000 feet you climb, the temperature drops 3.5 degrees. A single mountainside condenses the entire ecological transition from a temperate forest to the Arctic tundra into a day's hike. Surviving here requires highly specialized biology. The mountain goat, for example, relies on a hard outer hoof for gripping jagged edges, paired with a soft inner pad that acts like a climbing shoe to navigate sheer drops that would paralyze most mammals. The higher you go, the more punishing it gets for the human body. The air pressure drops, meaning every single breath delivers a fraction of the oxygen your bloodstream needs. Move up too quickly, and the body triggers acute mountain sickness, nausea, disorientation, and eventually fluid building up in the lungs and brain. The mountain's physical shape also violently disrupts air currents. The sheer walls force air upward, where it rapidly cools, loses its ability to hold moisture, and condenses into localized violent storms that arrive with terrifying speed by early afternoon. Between the freezing cold, the thin air, and the explosive weather, life in the alpine zone is balanced on a biological razor's edge. It is a highly specialized system with zero tolerance for instability. Up in this hostile environment, more snow falls in the winter than melts in the summer. Over decades, that surplus compresses under its own weight, squeezing trapped air pockets until it recrystallizes into dense ice. It becomes a glacier. These frozen rivers drag themselves downhill, carving massive U-shaped valleys directly into the bedrock. These glaciers and the surrounding snowpack function as enormous natural reservoirs. They capture and lock away intense winter precipitation, holding it high above the valleys. As temperatures rise, that ice provides a slow, steady release of water throughout spring and summer. Across the American West, this runoff fills the Colorado River, supplying drinking water, irrigating farmland, and generating hydroelectric power for millions of people. You don't have to ever set foot on a summit to rely on one. Cities hundreds of miles away are physically tethered to the health of these frozen rivers at the top of the world. We expect mountains to outlast us. It takes tens of millions of years for the Earth's tectonic plates to build a peak, but the ice and caps it can vanish in a single human lifetime. In 2010, Glacier National Park contained about 150 glaciers. Today, only a small fraction remain. You can stand in front of a barren ridge holding a century-old photograph and see the exact spot where a massive glacier used to be. This warming triggers a biological chain reaction. Small alpine animals like the American pika are highly sensitive to heat. As the lower slopes warm, their populations are forced to retreat higher and higher into the mountains until eventually they run out of elevation. Glaciers act as natural archives. As snow compresses into ice, it traps tiny air bubbles, perfectly preserving samples of the Earth's atmosphere. By extracting these ancient bubbles, scientists can precisely measure historical carbon dioxide concentrations, going back hundreds of thousands of years. Mountains function as the planet's early warning systems. Every retreating glacier and shifting population of wildlife is broadcasting a story about the future of the climate, one we must learn to read before the archive disappears entirely.